Hello, everyone, and welcome. We'll be starting our webinar in a few minutes. We're waiting for more attendees to join as we speak. Thank you very much first for joining us today. I hope that despite the COVID situation, you're all safe wherever you are on the globe. My name is Catherine Simondi, in charge of marketing and communication at ID Quantique, based in Geneva, Switzerland. This webinar is a part of a series we started a few months ago. It will be recorded and can be watched anytime on our website, just like many others we've done already. So don't hesitate to forward to other colleagues of yours once you get the replay. To let you know, we will have a Q&A session at the end of this webinar. So if you have any questions, please use the questions box on the platform on the right-hand side anytime, and we will answer at the end. Okay, so we're waiting just a few seconds. So our webinar is entitled Advanced Techniques for Characterizing Multi-Photon Quantum Interference and Entanglement. And you will learn how IDQ's technology can be used to simplify this task immensely and provide the necessary specifications to get optimal results. So with me today, we have Felix Bussière. Hello, Felix.
Hello, Catherine.
Felix is VP Research and Technology at IDQ. Felix and his team are responsible for the development of IDQ's core technologies and for key innovative projects. Felix obtained his PhD in physics from the University of Montreal. He then worked as a senior researcher at the University of Geneva in Switzerland, where he led research in quantum technologies. There, he played a key role in developing high-performance superconducting detectors. After joining IDQ in 2016, he took the superconducting detector technology from a prototype to a successful product line we'll be talking about. He now leads several innovation activities related to the development of single photon detectors, quantum random number generators, and quantum key distribution. And in his team with us today also, Gianluca Buzzo. Hello, Gianluca.
Hello.
So Gianluca is system architect at ID Quantique. He obtained his PhD in information technology from Politecnico di Milano in Italy, and he also joined IDQ in 2016, where he is one of the leading experts in single photon detectors and quantum key distribution. So let's start. Felix, the floor is all yours.
Great, thank you, Catherine. All right, so we'll be switching off the webcams during the presentation. So if you see us disappear, don't worry, we're still there. So thanks a lot for joining us today. We appreciate you spending the time with us. We want to tell you about advanced techniques for characterizing multi-photon quantum interference and entanglement. And let me start with an overview of what we want to talk about today. So let me start with what, how, and why. Okay, so what we want to talk about is these tools and techniques. How? Well, time tagging and time resolved measurements. These are the techniques that we're going to cover. And why? Well, combining these tools and these techniques, why you want to do that? Well, you're going to get simplicity. Hopefully will convince you that you can get some very good results and push the limits of your application. And importantly, focus on the science and not the programming. And during this, we're going to talk about some practical points. So practically, the tools we're going to talk about is mostly the time controller, a bit about SNSPDs. And we'll show you how you can easily get 2- to 4-fold coincidences with visual programming only. And then I want to spend a bit of time talking about the FPGA that's built in this time controller, just to show you that it's quite a powerful tool that is available for you to program with. I want to show you some real-time analysis and optimization features you can get with the system. The fact that it's easy to use, so you can set up things rapidly. And I want to talk about some LabVIEW customization. In terms of the audience, it's not only for quantum optics people, it's certainly for quantum optics people, but not only, because any kind of experiment that deals with detections and timing and logic and processing with these clicks will be concerned by this presentation here. So there are some applications of the same techniques for LiDAR and OTDR, for instance. I'll mention that later on. Okay, so I want to talk first about analyzing photon pair sources and two-photon entanglement. And I'm going to be talking specifically about this experiment here. So you see on the top left a paper that was published in 2019 by people at the University of Geneva and EPFL, and Farid Samara, who's the first author of this paper. You see him on the picture there in his lab, and we sat down together and explained to me how he's been using the time controller in that experiment. So this experiment is a source of entanglement based on micro-ring resonators, silicon nitride micro-ring resonators. So I'm not gonna spend time on the quantum optics part, but there are a few things that you need to know. First thing is creating photon pair sources. Perhaps you know already about. So sorry, let me just put the laser pointer here. Whoops, it doesn't appear. Okay, well, I'll be using the arrow like this. Hopefully you see it properly. It's just a bit unfortunate that I cannot make it appear. I'm surprised by this. Oh yeah, okay, I can make it appear here. Yeah, laser pointer. There you go. So you should see my laser pointer. So perhaps you know already about SPDC, spontaneous parametric down conversion. The idea there is to have a chi2 nonlinear medium that you pump with a pump photon, and then the medium is going to act as a converter, basically from one photon to a pair of photon, so that the energy is conserved and momentum is conserved as well. Well, that's not the only way to do that. You can also do that with the chi3 nonlinear medium. It's called spontaneous four-wave mixing, where two pump photons become annihilated to create an idler and a signal photon. And of course, here as well, the energy is conserved and the momentum is also conserved. So this is the type of source that I'm considering in that presentation. Okay, so bringing that idea here again, this chi3 medium, we get these two pump photons to get this idler and signal photon. And if we look at the source that Farid and his collaborators have been working on, it looks like this. You have a pump preparation stage, so CW or pulsed. Here I'm going to talk about mostly the CW case. This pumps this silicon nitride micro-ring resonator, which is a nice way of generating photon pairs. Actually, light comes in here, and it can couple in and out of this ring resonator, which is the chi3 medium, and then it forms a sort of cavity. So a photon that is created in there will already benefit from some kind of filtering, and that's going to be useful for quantum communication experiments. So when the photon pair is created at a random time, light is coming out, we reject the pump, they go through some analysis for entanglement, I'll be talking about that later, and then back out on the detection part. Okay, so this type of source is suited for integrated quantum photonics. This is a very small chip, and the hope is that everything else can also be put on chip, just to advance quantum technologies using photon pair sources. The photons are telecom, right? The two pump photons are 1557. The idler photon is at 1555, and the signal photon at 1558. So this kind of source is, because it's telecom, it's suited for long distance quantum communication, and the intrinsic filtering that you get there is good for quantum memories, absorption in quantum memories, quantum repeaters, and quantum networks. Okay, so if you want to analyze the entanglement there or analyze the photon pair source as it is, then you need to look at detection times there. You need to register these detection times and find a correlation between these times. So the kind of detector that was used in that experiment is SNSPD, superconducting nanowire single photon detector. I'll just give you one slide about these in this presentation. So they're devices that are cooled to 0.8 Kelvin in this cryostat here. They provide you with free running operations, so you don't need to gate them, so you can just leave them open until a photon arrives. you can get very high efficiencies, up to 90% and more. The noise can also be very low, 1 to 100 hertz or less. The jitter can be very good, 20 to 50 picoseconds, and the recovery times as well can be very short, 20 to 60 nanoseconds. And then the detection rates are typically in the tens of megahertz. And actually, we have a new kind of detector that can detect in the hundred of megahertz range. You also get an upside with these detectors. The efficiency can be really broadband, so it can be high over a range of hundreds of nanometers. You can have multiple channels in one cryostat, so we offer a 16-channel version of this. And then a new kind of detector as well that we're offering is able to do photon number resolution. Okay, so what do you get out there? Well, you get very good detectors, the best in terms of performance you can get. It's also a cost-effective solution for multiple solutions, and it's naturally suited for multi-photon experiments where the demands on the performance are really high. So if you want to know more about this, you can go on our website. We have a webinar that I made a few weeks ago that talks about these different things here. So you're welcome to go there and have a look at that. Okay, moving on to the main tool that I'm going to be talking about, the ID900 time controllers. It's a series of devices. Here I'm going to talk about the model called master, where everything is available on the device. So in a nutshell, it has starts and stops here. It has input and outputs. It has FPGA built-in processing. Okay, so here the inputs are precisely timed, and the outputs as well. And this FPGA is something very specific to this device. It provides the device with super high processing capability. So in a way, you could see that the FPGA and a time controller for processing of clicks in the detection in single photon or multi-photon experiment can have an effect that is tremendous. An analogy you can make is the effect of GPUs in computing. It really provides you with the tools to get to these high processing rates, but also we made it in such a way that it's easy to program. So if you want to know more about the series of the ID900, you can have a look at another webinar that's also on our website. Okay, so a bit more details. The inputs there have a jitter of 8 picosecond RMS. There's a counter stage that can count as high as gigahertz, and the device can process 100 mega events per second. So if we look at this in more detail, you can have an experiment generating clicks. It goes there. So we have the counter stage, the processing. We have in the device the ability to generate histograms inside. So you don't have to compute that yourself. You can just output the histogram instead of outputting the data. There's also outputs, delay generator with 100 picosecond precise trigger and delay generator, a low latency programmable and conditional output. So you can take these different inputs, make a processing, and actually output something there that can feed back into your experiment. So that's quite a unique feature of this device. Okay, so remember, I want to show you how you deal with this here. So you want to find these two photons there. And the two photons, they're created at the same time, but they are not necessarily getting there at the same time. Okay, so there's, of course, naturally some delay. So if you want to find a pair, you need to be able to adjust a delay between these two here and define a window into which you are expecting to find the second photon. So this one is a start and this one is a stop. So you need to play with this delay here and the width there to find the photon in your coincidence window. So let me just, I need to get rid of this pen here and get back to this here. So I have a little video to show you how it actually operates. Okay, let me just arrange this. Yes, all right, video started, sounds good. Okay, so the interface of the time control that you see there looks like that. Apologies, I need to make this disappear like that. Okay, let's go, let's restart again. So the interface looks like this, where first you define here your inputs. So here we activated inputs 2 and 3 and 1, but there's nothing connected to it. We already see the counting rate on inputs 2 and 3 there. And we go to the counters tab here, where we select what we want to see. So detectors 2 and 3 are used here. We remove the start. We're not going to use it here, and we don't need one. So we've defined it like that. This is defining the coincidence window that I was telling you about. We need to be able to do that. And the delays between the two channels are going to be set right here. This is the integration time of the counters, the counter history. You're going to see data start rolling off right here. The acquisition time, we set it to a very long time just to have it running continuously, and then it starts. Okay, we start seeing the counting rate there with this integration time, and we see the data rolling in, and then we look at the coincidence between channels 2 and 3, which are displayed right here. Okay, so we can change the width of the window in order to change the coincidences. Maybe it needs to be of a certain width to not have spurious data on the side. That affects the counting rate that you see there. If you display only the coincidence rate and you work in an optics lab where you have a computer from afar, you're trying to align everything, you play with your knobs on the optical table, well, this provides you with a big screen and the counting rate, and you can try to optimize the results that you have there. You can define how data is displayed. You can remove the auto zoom, change the scale vertically like this so that it makes things easier to obtain the signal you want to get, and play again with the coincidence window in order to, for instance, maximize the output that you have there. Okay, and you can round to the proper amount of number. If you have very large counting rates, it's quite useful to have this feature there. Okay, so now let's have a look under the hood a bit more. Okay, so I don't want you to get the wrong picture. We're not trying to sell you a Ferrari, but we are trying to sell you something that is super performant, that has a really, really great engine, and in a way, it's even better than a Ferrari because you can actually tune it yourself, which is not something that I would do if I would own a Ferrari. So for physicists, maybe one could argue that this is even more fun to have a time controller, but okay, I'll leave that for another debate. So here's another video where we see what's happening under the hood. Okay, so this is the FPGA. Okay, there's different blocks that you're going to connect together in order to do your processing. I'll explain in more details later how this actually works. Okay, so first thing you do is you communicate to the time controller and you load in this configuration editor the configuration that's already inside the time controller. So you load it there from the window at the bottom, and then it shows you things are connected in a certain way. So the first thing we want to do is to switch off channel 1 because we're not using it. And then we want to activate input 2. Okay, so you go on the right side, go to on and activate that. And do the same thing with input 3. And here we want to do a coincidence between input 2 and input 3. So when you move your mouse over, you see the connections between the different stages. It tells you, so input 3 goes there and so on, and you can see what happens inside the FPGA. Okay, and we want to use this window here, which is the block that's going to allow us to do a coincidence between channel 2 and 3. So channel 3 is connected. So you go there and you define how the coincidence window is actually being defined. And then here you see you change this and you have delay 2, which is connected to input 2, which goes into the start and the stop of the TSCO. So already now we have something connected to do a coincidence between channels 2 and 3. It's called a filter. It's called a time filter because it does more than a coincidence, but you can effectively use it for that. You can define the parameters there in order to define what it does, enable, and there you go. You have your coincidence window there. Okay. So now you want to display that. You can either go to raw data out or a histogram. Or the other thing you can do as well is you can go to an output. So you can define an output that is conditioned on this coincidence. So here, what we're doing is switching off or defining which combiner is going to be used as the input of that. We don't want 12, we want the 7 there where we have the coincidence between channels or input 2 and 3. So we change that. And you see that they're connected. Change the mode, activate the output pulse, and the width, we make it to 10,000 picoseconds. And you have this condition output that's going to click whenever you have a coincidence with the right timing between these two inputs there. All right, so for a 2-photon or a photon pair source, one of the first things you want to look at is the coincidence rate as a function of pump power. So you can get this coincidence rate directly from a histogram that is calculated or directly from counters inside the time controller. And then for this type of source based on spontaneous four-wave mixing, the coincidence rate should be increasing quadratically. And that's what we see there. We see two sources, pump power increases. We see this quadratic increase with pump power. So very easy to do only with visual programming. The other thing you want to look at is the cross correlation between the signal and idler. So if you know quantum optics, you know that if you look at the coincidence rate with as a function of the delay between one photon and the other, you're going to see a peak like this, and the shape depends on the spectral properties of your two photons. And then if you look at the ratio between this maximum there and the edges there, you're going to get the value of the cross correlation. When the pump power is small, so that the pair probability is small, this goes as 1 + 1 over p, p being proportional to pump power. And if p is very small, then this becomes a large number. It's the ratio between that, and that tells you that the source is non-classical, and you actually get an excellent photon pair source. So all of this only with visual programming. Another thing you want to look at is the unheralded autocorrelation of your source. So for this, you can ignore this idler photon and look only at the signal photon. You send it onto a beam splitter and then on two SNSPDs, and you can look at the coincidence histogram between these two here. This is going to tell you something about the statistics of this photon there. It's necessary for taking the source further. Okay, so the number you want to look at is this autocorrelation with a certain delay. And it turns out if you look at the correlation here with a 0-time delay, this is going to be equal to 1 + 1 over k, k being the number of modes. And if your source is pure, you have only one mode. And here it should give you a value of 2 for a thermal source. And that's actually what we see only with these histograms or counting rate in a time controller. That's what we see for this source of the experiment of Farid. It reaches almost 2. It's very, very close, meaning that the source is really, really good. And it's ready for a next step, for instance, an entanglement swapping operation. All of this is possible because it's a CW source, right? So it's possible because you have a very good resolution on SNSPD, 35 picosecond, less than that actually on SNSPDs, and a jitter forward half maximum of 20 picosecond on the time controller. All right, so the energy time entanglement you're going to get with that. I don't want to get into the details, but it will suffice to say that because the two photons are created at the same time, you get a superposition of the different possibilities. And that's because the pump is highly coherent. Getting that means that the photon pair is created at the same time, but at a time that is quantumly undefined, undetermined. So if you send these two photons in two interferometers, there are two paths that are going to be indistinguishable. It's both photons taking the short path and both photons taking the long path. And if you look at the coincidence rate there and the right timing, which is why you need the time tagging there and the processing, then they're going to interfere as a function of the phase that you have, the phase difference between the two interferometers. Okay, so that's what we want to be looking at with the time controller. And here I'm showing a video taken from Farid's experiment. Here what they did is they connected the LabVIEW program directly to the time controller. The time controller is doing all the processing. The LabVIEW program isn't. So it's just basically reading the data off the time controller. And they wanted to do that because they wanted to have a bunch of different histograms there. So what we're going to see here is the counting rate on the detectors. So these two detectors actually sum up to one detector. There's not, I see there are two inputs, but they sum up to one detector, and this is the second detector there. So the detection rates are above 300,000 detections per second. So I'm starting a video, and then what Farid is first doing is that he's using a reference signal to get a phase for destructive interference in this entanglement. And that's what we see there. The peak there is the one we want to be looking at, and it's close to minimal because the phase is set properly to get that. So now what Farid did right after that is he changed again the phase to get a constructive interference. So playing with the knob with this feedback signal there, he knows the value to get to this constructive interference, and then runs it again, and is going to get his constructive interference. So the peak at the center is now of close to the maximum value. So again, detection rate on one detector are more than 300. Same for the other one where we have the sum of these two. And that allows you to very quickly get the quality of the entanglement by looking at the ratio between this maximum and this minimum there. Again, so this program is only reading off the data computed by the time controller. All right, so there will be questions at the end, but if you have any questions so far, you can already enter them in the questions tab in the application of the GoToWebinar. So please don't hesitate to already input questions. So let's move on to 4-photon coincidence and entanglement swapping. So for this, I want to go further into the hood, under the hood of the FPGA. So the time controller has these discriminant stages there. Here, this is where we get the timing, and then we get the FPGA. So I showed this to you before. Let's look in more details what it has. So there's different levels. So signals go from left to right, and you can connect these different stages there. And here we have the discriminators, the counters. At this point, you have the delays and the event generators. I don't need to talk about this one here, but if you use the time controller, you understand why they're there. So we can set delays and windows. And here, this is where the processing happens. So we have 24 of these boxes there that are used for doing the processing. Okay, so these are the time filters to do the logic and the coincidences. These can go out into the timestamp generator to export to disk, or into the histogram generators that does the computing. And then everything, well, these boxes can actually connect it to the outputs that I mentioned initially. So you connect these blocks visually to define your own processing, and lots of room. You have lots of blocks to play with. So to do entanglement swapping, you would take two sources such as the one that I mentioned before. And if there's CW pump, the photon pairs are going to be created at random times. Okay, so in order to do swapping, you need to take photon pairs that have been created with the proper relative delay. Otherwise, you cannot do the swapping. Okay, so you need to post it like that using this station here. And you need the time controller in order to do that. Okay, so the detectors and the jitter have the right, the detectors and the time controller have a sufficiently small jitter in order to post-select the two pairs created at the proper relative time. So that when you do that, you look at a coincidence there, you do a twofold, and that will project the outer photons onto a Bell state, psi minus in this case, if you do this properly. Okay, so these two photons on the outer edges, they've never interacted directly with each other. They were created independently, but they end up entangled. Okay, and then they go through interferometers for analysis. And when you detect them, you can combine the output of that with that. So you can do a threefold, that which amounts to a fourfold overall. So that's a lot of, but actually in practice, you don't do that. You actually use twofold boxes. So a twofold here, the output of that is fed into a twofold between that and that detection. Same on that side here. And then we take these two here and we do a twofold, and you get the fourfold out of that. So this is a lot, this can be a very long measurement because of inefficiencies and so on. So you get a lot of singles and very few fourfold coincidences. And the time controller, to do this twofold between detectors 2 and 3, the middle station, the central station, you would use a combiner like that. So you get this AND gate there. You can display it on a histogram if you want. To to do a threefold with detector 1, you're going to take this, and here these are just bypasses, and you use this window here, this combiner here, in order to look at the or to get the threefold between the output of that and this one here. And you can input that as the start of a histogram. You can do the same with the other three here. So that's the second threefold. Same thing here. You have this going there, going into a window that is doing a coincidence between the output of that coincidence here, which implements a threefold, and that goes into the histogram as a stop. So then this histogram there is going to be looking at the relative histogram between these two threefolds, which is going to give you the histogram of the fourfold in total. You don't have to use the histogram. You can go to raw if you want, but the histogram is going to do the computation, and you don't have to output the data outside of the time controller. So you're not limited by the output rate of your connection to the computer. An interesting thing with the CW experiment, you also want to keep you want to keep the events where photon 2 arrived before photon 3, or the opposite, because that allows you to count twice as fast. And actually, you have lots of room in order to do that. You can define other boxes in order to do this here. So not just these one here, but this one here. And you can have a second histogram in order to do that. So there's room to do a bunch of other things, like looking at hive heralding efficiency, for instance. You can monitor if everything is proper. If you run out of boxes here, you can actually use raw and do computation in a computer. But of course, you want to pre-process so you don't have to transfer a lot of data on a computer. And you can even use conditioned outputs if necessary to do even more. We do provide you with generic examples. So this is an example where you have a fourfold, where the detection times of 2, 3, and 4 will be outputted as a relative to input 1. So this is how you would connect it. Everything goes in a first block and then a second block right there. And you can, if you program the time controller, you can start from a generic example there and actually adapt it to your actual experiment. Everything, again, can be done with visual programming. Okay, so I want to give you a glimpse into the versatility of this combiner block. So it can do a bunch of operations, not just an AND. It can do an OR it can let the first through or the second through only. These are from previous blocks, so input stage, delay, event generator, or a previous box like this one. And the window that defines the coincidence or the time filter can also be another block. Okay, so you can have a window that is dynamically changing. It's not always the same window. You can have something changing over time, and then your combiner will adapt to the previous fluctuations in the window that you may actually have. So it's a very powerful tool. And the output, you output it to the histogram or a raw data output. Okay, so how much data can be processed by the FPGA? If we were to do this entanglement swapping with sources such as this one, how much are we actually processing inside the FPGA? So with a detection rate of 300 events per second per detector, if we consider that writing at one timestamp onto the file requires 8 bytes, so here we have to process that many bytes per second. Okay, so an experiment like this running for an hour would have to process 34 gigabytes of data. Okay, that's 10 megabytes per second. And actually, we're not even close to the full processing power of the time controller, because it can process up to 100 mega events per second. That's 800 megabytes per second. So with the time controller, the lesson is do not transfer everything to this. Just use the power of the FPGA first. There's lots of room. It's easy to program, and just benefit from that, so that you just output histograms if you can output only histograms. And there's still further you want to do, well, you can still output raw data that is pre-processed, and use these outputs. Okay, so wrapping up, I'm just bringing the first slide that I had initially. Spoke about characterizing multi-photon entanglement. Well, the watts was tools and techniques to characterize that. quantum optics is not the only experiment or type of experiment that allows you to do that. Actually, LiDAR also can improve its signal-to-noise ratio by using coincidences. This is something I spoke about in another webinar. You can see it on our website. And this is also actually something we did ourselves in a previous project. I'm mentioning that, and we've been using the time controller in that experiment to improve the SNR of LiDAR. Same thing applies to OTDR actually. So we spoke about time tagging, time resolved measurements, and hopefully I was able to show you that you can do it simply, optimize the results, and even push the limits of your application, and it allows you to focus on the science and not the programming. We allow you to play with an FPGA without having to do any kind of FPGA program, which is hopefully will be of great value to you. So I spoke about time control and SNSPDs, how to do 2 to 4-fold coincidences with only programming. I hope that convinced you that the FPGA power is at your fingertips and can be useful for you for doing real-time analysis and optimization. The setup time of an experiment using the time control is greatly reduced because you don't have this programming to do, and it's customizable into LabVIEW, Python, and MATLAB. I want to say a big thank you to Farid and his colleagues that showed me how things were working and provided some data for this presentation. And before finishing, I just want to say a few words about IDQ. So we're a company where we want to provide trust in our devices. We've been founded, it was founded in 2002. We have 2 business units. We're going to provide you with high quality engineering, best-in-class performance, trust, and operational simplicity. This is a picture that was taken in Les Diablerets at a recent company event. Very nice place, so if you have a chance to go there, it's beautiful. And we're going to finish now. We're going to move on to questions, and I thank you very much for your attention.
So, hello, Felix.
Hi, Gianluca.
I'm receiving a few questions from the attendees. I know we don't have a lot of time for questions, so I try to wrap it up a bit. There are a few attendees that are asking about if and how we can use this instrument, so the time controller, with other kind of detectors. So you gave SNSPD as an example, but can we use it with other detectors? And does it have the same performance? So in terms of timing jitter, for example.
So absolutely, the jitter of the time controller, I mentioned 8 picosecond RMS. That's the device only, so it's very small. If you are considering other types of detectors like SPADs, the overall jitter of the system is going to be the convolution of the detector itself, whether it's a SPAD or an SNSPD with the time controller. So it doesn't change with the type of detector. The overall system does change, but the time controller itself doesn't change its jitter as a function or with different types of detectors. So, and yes, the performance of the time controller are just the same independently of the device. It can detect with the discrimination stage is very precise. You can adjust it at the millivolt level, and it has a bandwidth that is extremely high. I don't have the data offhand, sorry, but it can detect very short pulses there.
Okay, so the next question is going to be, okay, so you showed us some FPGA functionalities, so the time controller can do a lot of processing inside, but is it also possible to save the raw data and so to have the full picture of my experiment?
Absolutely. If you want, you can bypass everything that the FPGA can do for you in pre-processing. You can definitely transfer to the computer. Then what you have to consider is that the transfer to the computer will never be as fast as what the FPGA can process internally. It's super fast. So it's close, but it's not as fast. And then you also have to do your own processing afterwards with your computer, which is not as fast to do the processing. So you can certainly do it. It's just it makes your life easier if you use the FPGA directly. But you can totally do that if this is necessary for your experiment.
Okay, so another question is, can I use the functionality of the time controller as a signal generator? So can we use the output just as signal generator?
Absolutely. So I'm just going to move back to the slide where I mentioned this. It absolutely can. If you want, you can buy in the series of time controller. There's a version that is only doing the delay generator. So indeed, you can use it only for that. And the kind of precision you get is 100 picosecond precise. So the binning of the output signals is 100 picoseconds.
Okay. So another question, it's quite technical. They're asking us if we can use the output as conditional outputs. So for example, process some inputs and then generate an output that is conditional. And if it's fast enough to afterwards use it to control part of the experiment.
So the input-output delay between these and the output there is a few hundred nanoseconds. Okay, so it's not super short, but it's not that long either. So it really depends on what you want to do. So if you want to delay and do something on the photons, you're going to have to put the photons in some spool of optical fiber. That's expected. If you have something much smaller, you can absolutely do it. There are some experiments that don't require extremely fast conditional outputs. Maybe you just want to stop something, stop another measurement, or trigger a wave plate or something like that. When you do have a conditioned output, you could think of maybe a Bell state measurement. A Bell inequality measurement where you want to change something, you want to change the settings of your measurement whenever you did get a few clicks in a certain setting in order to randomize the results, and that's the kind of functionality that could be done using the time controller conditioned output.
Okay, so there's one of the attendees that maybe didn't really get the difference during the demo between what is the integration window and the coincidence window. So I think you showed some functionality in the time controller where you have the coincidence window, but then you can also change some integration. But I think it's referring to the integration time.
Okay, so I guess this is this here. So let me just bring this back. I'm going to move this a bit here. All right, so if we want to see a coincidence between channels 2 and 3, they may not arrive at the same time, even though like the photon pair, the two photons of a pair are created simultaneously, but they may not arrive at the same time. So in order to find this right window for a coincidence, then you're going to select the width of this window here and the relative delays until the window is properly positioned around the two photons that you want to pick. And the integration window there is essentially the refresh rate of these counters there. So if I just start it and move it to the point where we have it activated. So if you have a look here, this is the frequency of detection of input channel 2 in hertz. So this is 100,000. Well, this number here is refreshed 10 times per second because we have 100 milliseconds there. So it's 10 times less than that. So that's the integration time that I was mentioning. So hopefully that's the question that the attendee wanted to understand. Okay,
so from what I see, we are running a bit out of time. There are are a few more questions, but we can reply later. So we can send you an email, or you can contact us, and I think we can still have a chance to reply to all your questions. I see Catherine appeared in
Yes.
our screens.
Thank you. Okay, so we're going to end with a poll. I'm going to send it now. There we go. If you kindly can reply to this first question, is this technology relevant to your activities? That'd be great. I see, I'm collecting the votes. Wonderful. Thank you. And a second question now, which is the final one. And there we go. Did this presentation reach your expectations? Of course, we hope it did. So everyone's voting. Great. It's 100% yes. Thank you, everyone. So, well, thank you again, everyone, for taking time for attending. And thank you, Felix. Thank you, Gianluca. To let you know that our next webinar will be, there will probably be one in July, but there's already one programmed on August the 19th, organized in collaboration with DLR, the German Aerospace Center. It'll be on IC inspection. The title of the webinar is IC inspection and failure analysis using single photon detection. We hope you will be joining too. We will be sending the link probably tomorrow to you. Thank you again, everyone, and wish you a lovely end of the day. Bye-bye.
Thank you. Bye.